In this video, we're going to talk about how flexible your model should be. For example, how many polynomial features should be used? To understand this, we will discuss one of the major theoretical results in machine learning, the bias variance decomposition. We will also discuss overfitting, underfitting, and how to fix these issues. One idea you may have is to add as many polynomial features as possible. After all, the more polynomials we add, the more flexible our model becomes and the more we can fit. So let's always use as much flexibility as possible, right? The more polynomials, the better. Now here's a question for you. Why is this not always a good idea? Please pause the video for a moment and think about this. Afterward, we discuss the answer. Okay, welcome back. The answer is we risk overfitting. This means the model works well on the training data, but it doesn't work well on unseen test data. And this was the ultimate goal of machine learning, to work well on new data. Thus, memorizing the training set is not always a good idea. Here in the figure, I have indicated a red arrow, where you can see the green line is really memorizing a point that has nothing to do with the underlying regression function. It is only fitting noise, or with other words, overfitting. In this video, we will discuss on a deeper level what is overfitting and underfitting and how can we understand what is happening. Finally, we will discuss how to fix these issues. Let us start with the bias variance trade-off. This is one of the fundamental theoretical results of machine learning, and it is given by this equation. Let us see what is in this equation. On the left-hand side, we have the generalization error in terms of the mean squared error. Here, y0 is the true label of a new unseen object. F hat is the prediction of our model for the corresponding feature vector x0. We subtract and square them to get to the mean squared error. The capital E denotes the expectation over the data. You can think of this as the error on a very large unseen test dataset. We see that this term is decomposed into three terms. The first term is called the variance. What do we mean by that? Well, this means how much the model changes when you retrain it on new data. The new data is gathered in the same way as the data that you currently have. So we receive data from the same underlying problem or population. The second term is called the bias. What does this mean? The bias means the error introduced by the approximation of your model. For example, maybe the underlying function that you try to find is quadratic, but instead you use a linear model. In this case, using a linear model introduces an approximation error. The third term is the irreducible error. This is noise you can never get rid of, no matter what model you choose. It is inherent to the randomness of the world. Because of this noise, we cannot make a perfect prediction. It could be related to noise in your features, or it can account for things we may not even have measured, or that we do not know about. Note, that this is called the bias variance trade-off for historical reasons. However, it does not mean you always have to trade one term for the other. In some cases, you can make all terms small. So trade-off is a bit of a misnomer. Finally, you should note that this equation holds for the mean squared error. If you care about classification, a similar trade-off exists for the error rate, but we don't go into that here. Okay, let's look at some examples to illustrate this equation. We're going to discuss the following regression functions on the left. Let us start with the orange model that is a straight line. Note that the true pattern is given by the black line. Now the question is, does this model, the orange line, have a low or high variance, and does it have a low or high bias? For this example, let us discuss the answers together. Okay, so variance meant how much the model changes when trained on new data. So does this orange line have a low or high variance? Well, if we get some new data, we will roughly obtain the same line. Why is that the case? Well, because this straight line will not wiggle around a lot. It is not so much influenced by individual data points over here. On the other hand, we say it has a high bias. Why? Well, the true trend is given by this black line. And you can see it's actually non-linear. So our linear approximation here is too strong. It does not capture the real trend well. So we have a high bias because we have a large approximation error. In this case, the bias is the limiting factor in our performance. We call this situation underfitting. Underfitting means our model is too simple. The model is so simple we cannot even fit it well to the training data. Therefore, this case is characterized by a high training error. Now let us talk about the green model as a second example. To test your understanding, I have two questions for you. Does the green model have a high or low variance? And does it have a high or low bias? Please pause the video and take a moment to think about this. Afterward, we discuss the answer together. Okay, welcome back. We see the green model is this very wiggly line that is highly fluctuating. This means that the model has a high variance. Why? Well, imagine we get a slightly different data sets where the points have moved a bit around. If we now fit the green model again, the line will completely change because it is heavily affected by each point. So the line will be almost completely different. Therefore, the variance is large. On the other hand, the bias is small. Why? Well, you can see this model is flexible enough to fit the true pattern, the black line. So green has a low bias and it has a high variance. In this case, the variance is the limiting factor in the performance. This case is called overfitting. In this case, the model performs very well on the training set, where it has a small train error. However, on unseen test data, the error will be large. Okay, now we have seen these examples. Let's talk about what influences the variance. Remember, variance is how much the model changes when training on new data. I have 3 true-false questions for you. I think by now you have enough information to answer these questions. Take some time to think about them and be sure to write down your reasoning. So please pause the video and afterward we discuss the answers together. Okay, welcome back. Let's discuss the answers. The first question is, a higher degree polynomial increases the variance. True or false? The answer is true. If we go to a higher degree polynomial, we get a more flexible model. And that means we can fit more noise. We are becoming more wiggly. So if we retrain, probably your model is going to be very different. So this increases your variance. This is also called the curse of dimensionality. If you add more features or more polynomials, this can lead to more overfitting. So more is not always better. Okay, now let's go to question 2. A dataset with more noise increases the variance. True or false? The answer is true. If you add more noise, the training data will vary more. So the model is also going to change more. And because of this reason, our variance increases. Okay, then we come to question number 3. It is a larger training set increases the variance. True or false? The answer is false. The bigger our training set, the smaller our variance. Why? Well, if we have more training data, our model will average out more noise. Thus, the model will be more stable and it will be fitted better. Therefore, it will estimate the true pattern also more accurately. Because of that reason, we get a lower variance. So in conclusion, how can we decrease our variance? Well, there are 3 ways. We can increase the amount of data, or if it's possible, we can try to decrease our amount of noise. Furthermore, a higher degree polynomial increases our variance. Therefore, a lower degree polynomial or less features decreases our variance. Okay, now we have discussed the variance. Now let's talk about the bias. Recall that the bias is the error introduced by the approximation of our model. Again, I have 3 true-false questions for you. Take some time to think about them and be sure to write down your answers and your reasoning. So please pause the video again and afterward we discuss the answers. Okay, welcome back. Let us discuss the answers. The first question is, a higher degree polynomial decreases the bias. True or false? The answer is true. Why? Well, the more polynomials we have, the complexer our model becomes. Therefore, we can more accurately fit the true pattern. Thus, the approximation error of our model is decreasing. Let us now move to the second question. Adding more features decreases the bias. True or false? Okay, we have to assume here that the features are non-garbage features. That meant that features are actually useful for our prediction task. The answer here is true. The more features we have, the more information we have. Thus, we can better approximate the true pattern. So this reduces the bias. Let us now move on to the final question. A larger training set decreases the bias. True or false? The answer is false. Usually, the amount of data does not influence the bias of a learning algorithm at all. For example, the number of features or the polynomial degree does not change if we only add more data. Here we assume the complexity of our model is fixed and not changing. If the complexity or the amount of features would be tuned after adding more data, the situation could be different. Okay, let's summarize this video. We have seen that the generalization error can be decomposed into 3 terms: the bias, the variance, and the irreducible error. We discussed the definition of overfitting. It means we have a high variance, a low bias, and that the model is too complex. We can detect overfitting by a low train error and a high test error. Underfitting means we have a small variance and a high bias, and that the model is too simple. We can detect it by a high train error. We have also discussed several solutions to fix overfitting. First of all, we can switch to a simpler model. This can be accomplished by using less polynomial features or less features in general. We can also try to reduce the noise in our data or add more training data. To fix underfitting, we instead need a more complex model. This can be accomplished by using polynomial with a higher degree. Or we can also try to add more features.